Good morning, everyone. I'm Chialing Wei, and I'm happy to share my first project in my PhD. So I wrote this paper with my research partner, Mohit, and our supervisor, Dr. Czerniawski. And we are from Arizona State University. And this project's title is Automated Wall Detection in 2D CAD drawings to create digital 3D models. So for today's outline, I'll talk about the research background and experiment in our future research. So we all know the 3D model is very important nowadays because we can use BIM model for a lot of application analysis. However, the process of creating these 3D models is usually time consuming because we manually modeling this process. So we are trying to automate and speed up this process using computer vision techniques. So the possible input for the neural network could be the 2D drawings, or we take a slice of the point cloud into project to 2D, or the 3D point cloud. And we can use all of that input to do the object detection or a semantic segmentation task. And here's the answer. Here's the question we are trying to answer is that how neural network can communicate with the commercial software, which implies interoperability. So in our first approach was trying to set an experiment. We set the input as the 2D drawings because the 2D input is easier to implement and most owner has these documents. Secondly, we choose the object detection, wall detection text because we think the shape of the walls align with the bounding box output. And the last one, we choose Blender as our commercial software to create 3D models. So the process of our experiment is training and inference. And the last part is to reconstruct these 3D models in a software. So the first step of our training is to manually label our data because it's a supervised learning. Speaking of our data set is the ASU 2D drawings. So for each drawing is 3,400 by 2,200 pixels for each sheet. And totally we have 29 sheets. So to fit into our neural network, we cannot fit the entire sheets because it's too big. So we need to do the random cropping into a small crops, which has 256 by 256 pixels. And totally we have 2,900 crops for our entire set. After we have done that, we can separate the images to two folders. The first folder contains the images with wall objects and the other doesn't. So after we have these two folders, we can train a binary classification task using ResNet 50 models. This is some hyperparameters, and we use transfer learning and early stopping techniques. And we can use our first folder, which contains the small crops with wall objects to train a wall detection task using YOLO version 4 model. And we also use the transfer learning and early stopping techniques. And this graph shows the loss and epochs relationship. And the trend seems loss goes down through the epochs. And here's some statistical results. The precision recall curve, and we got 78% mean average precision for our test set. After we finish the training pipeline, we can start to infer the new drawings the model haven't seen before. And the first step is also to do a sequence cropping to the 256 by 256 small crops. So it's showing like this. We do a sequence cropping for the entire sheet. So after we do the cropping, we can we can use it as an input to our ResNet 50 model we trained before. And the output will separate those images to different groups, which contains wall objects or not. And then we use the images which contains walls to fit into our YOLO version 4 model. And it will output the bounding box location and the probability prediction of the walls. It will look like this. So we store the information to the CSV file, and for both coordinates and the prediction probability. And for visualization, look at the right-hand side, there's the original small crop and the bounding box around each walls and the class of walls and the probability prediction. And the last step is to combine all the crops back to the original sheet. It will look like this. And we found out that there are some failure cases. For example, the diagonal walls and curved walls. So even though we think the shape of the walls align with the bounding box, there are still some cases it's not suitable for bounding box, since the diagonal wall and curved wall is not good for bounding box label, that kind of rectangle labels. So now we can start to reconstruct our model. After we got this CSV file, we need to do some post process. And the first post process is to transform from the small crop coordinates to the entire sheet coordinates. So for example, this is the coordinates of the small crops, and it will correspond to these numbers in an entire sheet. And the next post process is to connect the wall spanning multiple crops. So take these walls as an example. Since we are doing small crops, so it will look like this, but actually it's just a single wall. So we do some calculation as to automatically generate just a single wall like this. So this is the picture before post-process, and this is after post-process. And the next step is to add the third dimensions, because we want to generate in the 3D model. So we add the third dimension. And after the post-processing, we can start to generate our 3D models in the commercial software, which is Blender. So we wrote a script in the Blender to generate these wall objects. So in detail, this is our CSV file. It has the wall type, IFC classes, X, Y, Z coordinates, and then height, width for each walls. And this is the script in the Blender. So we read our CSV file, and we get the X, Y, Z coordinates and read the dimensions. So after this, we can get the IFC file wall 3D models in the Blender. So this is some examples. These are the example which contains the 3 floors in this building. So for our future research, we want to do some research on the failure mode analysis. So what kind of training data will cause our neural network failure? So like these cases, what I mentioned before, even though we have some assumption that this kind of walls shape is aligned with the bounding box, but it still have some failure cases. So we want to explore more different inputs, like other, not only 2D drawings, like the point cloud project to 2D or the 3D points clouds, and different computer vision techniques, not only for wall, but the floor, the doors or windows openings, and using different models to see how this affect the neural network failure. So I'll end my presentation here, and this is my contact information. I'm happy to receive any feedback, questions. Thank you for listening.
Thank you for the presentation. So we will now have the Q&A. Any questions from the audience? Great.
Hi.
Hi.
Interesting presentation. I am Varun from IIT Madras. I have two questions. First, could you please elaborate more on what neural network you used for this? Like you said YOLO V4, right?
Yeah,
Yeah.
for wall detection.
For wall detection.
Yeah.
And in training, did you give curved walls and diagonal walls as inputs, like while training the classifier?
No, I didn't put that. So when I look at our data set, I found out that like curved wall and a diagonal wall is not, because since I think it's hard to label it.
I'm asking in the training, while training, giving the training data, where the curved walls and the diagonal walls were the part of training data?
Yeah, it's part of the training data, but I didn't label that.
Okay.
Yeah.
Okay.
So
you didn't label them as a walls.
Yeah, since I think if you label a bounding box here, it will cover too much background.
Okay.
So yeah, after this exercise, I'm thinking about maybe we can do some semantic segmentation for that part, because you label pixel by pixel is more suitable for those kind of walls.
Right. And one last thing, I see that most of the walls are being predicted as walls in the final way. Were some other elements predicted as the walls in the drawings, which were present in the drawings, like windows or doors, junctions are predicted as walls?
Yeah, so I think it's affected by how I label that.
Okay.
So I usually just label it from, for example, I just label like this is a single wall.
Oh, means you have taken even the window as a part of the wall.
Yeah.
Okay, for now.
So I think for the future research, I want to explore, like expand this to predict also the walls and windows.
Okay, I think then the resolution of the window you are selecting 256 by 256 shall be much lower of what it is now, right?
You mean like?
Yeah, so currently I think the wall plus the door is the part of the frame, right?
Yeah.
If you are planning to do further on a microscopic level, for example, a door or window, either you have to put the window exactly of the size of that, because otherwise, if you label that as a wall, then you are labeling window plus wall as a wall.
Yeah. Okay. Thank you.
Thank you. Nice presentation.
Johnny, very interesting work. There's a range of companies that would be interested in this, from startups that are working on automated takeoff to blue beams of the world to companies that are actually focusing on payment application for contractors. So there's a lot of benefit to this work. I have two sort of questions. One is a little bit more on the technical side. One is a little bit on the application side of it. On the technical side, it seems you've trained a model that does detection, right?
Yeah.
As opposed to segmentation.
Yes.
And it begs the question of the accuracy of your localization. How accurately the objects that are being detected are being localized in the 2D drawing. And I'm guessing that may make an impact on potential usage of the method for takeoff. Can you speak to what is sort of the accuracy of the localization of the algorithm?
Okay.
Considering that these drawings are all in some unit of measure, right? Roughly, are we looking at millimeters? Are we sort of thinking about centimeter error in localization? So that's my first question. Second one is on the more practical side of it. I'm wondering if you've started thinking about maybe segmentation methods, and if so, what kinds of walls have you been focusing on? It seems examples are primarily dry walls.
Yeah.
And I'm wondering if you want to expand this into takeoff applications, would you consider looking to details? And if so, how would you deal with training intra-class and inter-class variabilities in the categories? So 2 questions. One is on accuracy of localization and its impact on accuracy of takeoff. Second
Okay.
one is on segmentation and variability of different types of walls.
Okay, so so I hope I can answer the first question correct. So for this is our Euro version 4 model, and this is the model loss with APOX relationship. This is the trend and validation plot. And for this is the training loss and the validation loss. So each total loss is combined by the GIOU loss and confidence loss and probability loss. So I think the location of the prediction is related to GIOU loss. So it's like is similar to the IOU calculation. So how is the true location and the prediction location, the overlap part divided by the.
So what was the IOU used for detection? Was it 50% overlap between ground truth versus prediction?
If the
50%?
threshold, yeah.
Mhm. Okay, so that might make an impact on the accuracy of localization. Okay,
Okay.
great.
Yeah.
And what about interclass variability of walls? And
Yeah,
how you
so-
would approach training?
Yeah, so my supervisor and I are thinking about like explore different kinds of walls, like is common use in like in the industry. So maybe it can be like different types of walls, or like this, for example, this wall are connected with how many windows or how many doors, or like surrounding the furniture or something will affect this kind of prediction. Yeah, so like different configuration or different types of walls like that.